Before the official imaging campaign began, the ground team carried out a dense sequence of rehearsals to make sure every subsystem and every person involved would be ready for the short, unforgiving window when 3I Atlas passed within range. 2 full days ahead of the main attempt, they scheduled a set of child shots of the object, trial captures designed to verify its apparent orbit, test tracking performance, and refine the settings of TM1's high-resolution camera. Those early test runs on October 1st and 2nd were not treated as casual practice. They were a controlled calibration exercise in which engineers compared predicted pointing solutions against reality, evaluated how the target drifted across the field, and iterated on exposure times and stabilization routines. By the time October 3rd arrived, the orbiter was not improvising. It was executing a plan that had already been tuned against the object's real motion, which allowed the camera to be optimized precisely at the moment 3I Atlas reached its closest point to Mars. Using data from the earlier trials, the team adjusted the imaging pipeline for maximum clarity, squeezing out the most detailed views possible and producing final shots that were immediately described as stunning. Yet those images did more than satisfy technical expectations. They ignited a fresh wave of scientific debate, because the object they revealed looked less like an ordinary comet and more like something that defied clean classification. For months prior, 3I Atlas had been tracked quietly while interest mounted in observatories across the world, but neither NASA nor China released any significant new findings. Positional updates continued, but imagery and deeper analysis did not, and the prolonged silence became conspicuous against the background of rising excitement. Then, without warning, the quiet ended. On November 6th, NASA issued a brief but startling announcement. Long-range instruments had detected an anomaly in the object's tail with patterns of motion and brightness that did not align with known comet behavior. The timing was striking, because less than a day later China released the first publicly available images from its Mars orbiter's high-resolution camera, and in doing so described the object not as a comet or asteroid, but as a visitor. The closeness of the two disclosures, the abruptness after months of withholding, and the unusual terminology immediately raised questions about motive and meaning. Was this simply a case of scientific competition, one agency responding to another to avoid being seen as secretive? Or did both nations experience a genuine shift in what they believed the data were implying, prompting a near-simultaneous decision to go public? Whatever the reason, the synchronization was hard to ignore. The object itself offered no easy answers. By this stage in its passage, it barely shone at magnitude 6.7, fainter than what most people can see with the naked eye, which typically tops out near magnitude 6, making it a fast and faint target, the kind that pushes instrumentation and tracking software to their limits. NASA's November statement, though short, carried major implications. According to the report, long-range spectrographic and photometric observations revealed irregularities in the tail that could not be neatly explained by standard sublimation physics. In a normal comet, solar heating drives volatile gases to outgas in jets. Those jets push dust outward and form a tail whose shape and brightness vary in predictable ways with solar distance and rotational phase. With 3I Atlas, however, tail intensity fluctuated without any corresponding change in how close the object was to the sun or how it was expected to be rotating. The tail appeared to brighten and fade in a pattern that did not match the known rhythm of comet activity, implying some other mechanism was at play. Researchers inside and outside NASA noted that this lent weight to earlier predictions by astrophysicist Avi Loeb, who had argued that 3I Atlas, like the interstellar object 1I/Oumuamua before it, might be showing non-gravitational acceleration. Loeb's argument centered on a small but measurable deviation in trajectory that could be caused by solar radiation pressure if the object had an unusually high surface area-to-mass ratio. In other words, a very thin structure, something sail-like or panel-like, would be pushed by sunlight more than a compact, rocky body of the same mass. NASA did not endorse this interpretation outright, and its wording was notably cautious, but by confirming that the anomaly existed and was instrumentally observed. The agency effectively reopened the discussion that had simmered since the object's discovery. The report offered no images or detailed plots, only a summary of readings, and repeatedly emphasized that further analysis was needed before conclusions could be drawn. Still, the release itself represented a major shift. For nearly half a year, NASA's public messaging had treated 3I Atlas as a routine, if interesting, interstellar visitor, focusing on its hyperbolic orbit and updating its position as it sped through the solar system. Suddenly, the object returned to headlines not because of where it was going, but because of what it was doing in ways scientists could not yet explain. China's response, arriving almost immediately afterward, added another layer. The Chinese National Space Administration published 3 images captured near Mars, faint and low contrast but provocative. Astronomers worldwide scrutinized them, noting that the object appeared irregular in shape, showing asymmetric reflectivity and lacking the diffuse halo typically expected around the nucleus of an active comet. Some observers described the reflections as specular, mirror-like glints rather than the soft scatter of dusty ice, suggesting either a smooth surface, a metallic composition, or a geometry that caused light to concentrate in narrow flashes. The accompanying Chinese statement was almost as interesting as the imagery. Instead of comfortably labeling the object a comet or asteroid, it described it as a visitor from interstellar space, a phrase that sidestepped conventional taxonomy. Chinese scientists added that preliminary light curve analysis pointed to an uneven surface and possibly variable orientation, but they declined to speculate beyond that. Even so, the deliberate choice of the word visitor drew attention from journalists and linguists as much as from astrophysicists, because it carried a tone of distinctness, not merely an object passing through, but something arriving from elsewhere in a way that invited curiosity. When the two announcements are compared, their overlap and divergence become revealing. NASA focused on physical dynamics, tail behavior, radiation pressure, energy distribution, and the mismatch with sublimation models, while China highlighted optical properties and structure as suggested by imaging. Together, they painted a picture of an object that does not fit neatly into known categories. Neither data set alone proves anything extraordinary, and both agencies stressed uncertainty, but their convergence on unusual behavior intensified global interest. To understand why, it helps to recall what 3I Atlas is and how little is actually known about it. Detected in early 2024, it became only the 3rd confirmed interstellar object observed passing through our solar system, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Like its predecessors, 3I Atlas entered on a hyperbolic trajectory, meaning it is not gravitationally bound to the Sun and will eventually exit back into interstellar space. Early orbital solutions suggested a highly elongated path that cut inward from the direction of the constellation Cygnus, as some preliminary tracking indicated, before bending around Mars' orbital region and heading outward. Initial observations classified it as a comet because it seemed to carry a faint tail and spectral hints of volatiles. But as additional data arrived, that view grew complicated. The rate of brightness change did not match what outgassing models predicted, and its velocity profile showed small but persistent deviations from purely gravitational motion. By mid-2024, enough observatories had recorded these irregularities to confirm that they were real, not noise. Yet despite the mounting curiosity, neither NASA nor China released imagery for months, citing calibration and verification needs. In isolation, that justification was plausible. Faint, fast interstellar objects pose severe imaging challenges, and premature release can mislead. But the prolonged silence from both agencies, followed by an almost simultaneous break in November, inevitably felt reactive, if not coordinated. Several interpretations emerged. One was that NASA's anomaly confirmation forced China to publish its own images quickly in order not to appear as though it were withholding information. Another was that both agencies independently recognized the same kind of strangeness and chose roughly the same time to go public because the object was rapidly leaving optimal range. A third, more speculative idea suggested that a newly detected signal, perhaps radar echoes, unexpected spectral features, or a subtle trajectory change, created a threshold moment for disclosure. No evidence publicly confirms any one of these motives, but the closeness of timing keeps all of them alive. The underlying driver of the fascination is simple. 3I Atlas exhibits physical anomalies that challenge current models. Reports indicate that its tail does not consistently align away from the sun, a basic expectation for cometary dust tails powered by solar heating and wind. Instead, the tail seems to shift orientation periodically, as though responding to variable reflective surfaces, internal activity that is not thermal, or some structural feature that alters how sunlight and plasma interact with it. Meanwhile, the brightness of the central region fluctuates with a periodicity that does not line up cleanly with rotation alone, hinting at wobble, tumbling, or changing surface properties. Some compositional data suggest a spectral slope more indicative of metal-rich material and lacking the organic signatures common in icy bodies, though those inferences remain tentative. These features strongly echo the debate around Oumuamua. That earlier interstellar object showed non-gravitational acceleration without visible outgassing, and its extreme elongation, possibly even a flattened, pancake-like geometry, made it behave in ways that invited exotic explanations. Most astronomers at the time leaned toward natural scenarios, including fragments of nitrogen ice or hydrogen-rich bodies shaped by rare processes, but no single natural model fit all observations perfectly. Loeb argued then, and argues now, that the simplest explanation should not be dismissed merely because it is extraordinary. A thin, reflective, non-outgassing structure pushed by sunlight is exactly what a solar sail would do. With 3I Atlas, the stakes feel higher because the data are richer. Unlike Oumuamua, which was already receding quickly by the time telescopes pivoted toward it, 3I Atlas came close enough to Mars to be imaged directly by high-resolution cameras. That proximity, combined with NASA's tail anomaly data and China's optical imaging, gives scientists a clearer, though still incomplete, picture. If its reflective properties are truly metallic and its acceleration is independent of mass loss, it might represent a new class of interstellar phenomenon, or it might be an artifact. This possibility fuels both public intrigue and institutional caution. The idea of artificial origin is not presented as proof, but as a logical branch of inference from the evidence. A thin, light-reflective object that accelerates slightly under sunlight without clear outgassing fits the physics of a sail or panel. If another civilization had developed spacefaring technology long ago, derelict fragments or probes could drift between stars the way debris from human missions will one day do. Loeb's framework, notably, does not require that such objects be active spacecraft. They could simply be relics, technological fossils of exploration. Even so, skepticism remains the default position for many astronomers, and for good reason. Current data are limited by distance, faintness, and short observational baselines. Irregular brightness could arise from natural surface texture, complex tumbling, or patchy volatiles that behave unpredictably. Tail anomalies might stem from microimpacts, electrostatic effects, or magnetic interactions not yet incorporated into standard comet models. Without close-range spectroscopy or imagery detailed enough to resolve surface structure, definitive conclusions remain unreachable. Both NASA and China have acknowledged this uncertainty, and both have also noted a practical obstacle. 3I Atlas is now receding beyond the inner solar system, leaving the best observational geometry behind. Independent observatories have started publishing their own analyses, especially light curve studies, and many agree the behavior is unusual even if they disagree on interpretation. Meanwhile, public pressure for transparency has grown. Science outlets and major media have reported demands that NASA release all imaging data, including any possible captures from the James Webb Space Telescope, arguing that delay only amplifies speculative narratives. NASA has responded that processing and validation take time, but critics counter that openness helps science move faster, not slower. China has not offered additional classification beyond visitor, but the word itself continues to ripple through discourse, alternately framed as a cultural flourish of curiosity and as an intentional signal that Chinese researchers consider the object distinct from familiar natural bodies. As the months progress,